Okay, start by grabbing the geometry of a circle packet. A lot of this in the beginning should be all review. We've talked about a circle before. We've also spoke about a radius before, and that would be like OB, that segment. But there's multiple radius around here. There's OA, OC. All those are considered a radius. Diameter would be from one side to the other. So let's say a radius was 5. All these radii would be 5. Diameter would be 2 of those, which would be 10. The only diameter that we have here looks like CB. And we could write it CB or we could write it BC. It doesn't matter, backwards or forwards. A point on the inside I would say would be like EO. A point on the outside would be not necessarily like A or B or C because they're on the circle. We're talking about outside, exterior, would be D. The only one is this guy out here. All radii of the same circle are equal. Make sure you put your name at the top of this packet because we don't want to keep giving you a new one each time. Couple of things that should be new is what is a central angle? So a central angle is where the vertex is right at the center here. So like AOB, that angle would be considered a central angle. Another angle would be this angle here, AOC. And actually this is an angle too. It's called a straight angle. Be 180 degrees. That would be COB or BOC. Something new, and it's kind of neat, is what we would do with an arc. An arc is a part of the circle. So like from here to here, that curve is called an arc. And how we actually talk about it is we don't want to say AB with a line over the top because that means it's a segment. If we want it to be a curved piece, we actually put a curve over it or like a little rainbow over it. If we were speaking about from A to B, or I'm sorry, A to D, with a little curve over it or a little rainbow over it. Now if you look over here, I kind of made, there's actually two ways to get from A to D. There's this way, the short way, which we call the minor arc. And there's the long way around, this big arc around here, A to D. We call it the major arc. Now the problem is it's still A to D. So how should we write it? If we wanted to go from A to D, but the long way around, we'll give you another letter that you're going to hit along the way, like C. And put an arc over all of those. So ACD would mean you'd go the long way around, connecting A to C and then D. AD would mean the short way, the minor arc way. And we wouldn't have any letters in the middle between there. Something we talked about up top here is a semicircle. And a semicircle is just half of a circle. And it's the arc of half of the circle. So like from E to B. It's not the segment connecting E to B, it's the arc connecting E to B. That's why I put a little rainbow over it. And it's also 180 degrees. So flip the page and we're going to do one little part next. The degree measure of an arc. So if we have this angle in here that's maybe 60 degrees, we actually measure this portion of the circle and we can call it 60 degrees as well. Because if you think about it, we just talked about this part being a semicircle and being 180. It's 180 degrees in its central angle. It's also 180 degrees in its arc. So we actually measure arcs by angles as well. We can measure them by length too. We'll do that later. Now, hopefully you remember when we talked about going around an entire circle, it's 360 degrees total. So if we have 60 already and 180, that should leave us with 120 to be this remaining arc from here to here. Now it makes sense too because 60 in this angle seem like they have to make 180, which would make this 120. And if the central arc or angle equals 120, then the arc equals the same degree. The central angle always equals the arc. If you have circles that have both a radius of 6, like this, these circles have to be identical. So if one of these angles is 100 and this angle is supposed to be congruent to it, that would also be 100. This arc would be 100. And how much left would be the major arc here from G to E? There's 360 total. We've already used 100. So we can have numbers that are bigger than 180 degrees for angles as well. This angle here, inside here, is bigger than 180 degrees. We're going to use 260 degrees for its angle and 260 degrees for its arc, that major arc. And if this angle, or if this side doubles, these triangles are still similar because they're dilations of each other. This must be a dilation of 2, of a scale factor of 2, and it would double the arc. It also, or double the radius. It would also double the diameter. Now, if the angles were in there, it's just like everything else. Let's say that was maybe 120. The angles inside can't be doubled because it's still got to be 360 degrees inside. So let's talk about a proof for a second. AOB, if we want to try to prove these two triangles congruent, we still have our statements, we still have our reasons. AB is congruent to BC. That's given, and let's mark it. AB, BC. So let's see, anything else that we can do here? Well, hopefully you're looking at these two triangles and saying, well, they do share that in the middle. So mark it with an X. It's the reflexive property. And that's BO is congruent to BO. Let's see, can we prove these lengths are the same? They look to me like they're both radius or radii. AO is congruent to CO. Now you can word it however you want. You can look back on the previous page and see how we said it. But I believe one of the things that we said is like all radii. You could put radius, it's okay. In if you want to draw a circle, are congruent. And we've got it. The two triangles are congruent. We've got a side, and a side marked.